hope all is going well for you now and you're making progress in the probability. We're going to look at our last two sections, 11.6 and 11.7, and then we'll get into statistics, which makes application and use of the concepts we've come up with in probability. So 11.6, we're going to be dealing with There we go. Probabilities of something not happening, something or happening, this or that. So there's actually, you're going to see kind of increases. We get both of them, addition. And then something called odds, which typically people will think of probability and odds almost in the same breath. But we're going to see there's an important difference between the two. So let's go ahead and get started. So our objectives, we're going to find not probabilities, we're going to find or probabilities, and then we're also going to understand how odds is a different way of counting than probability itself. So we get a lot of notation here, but this is, let's just give an example. If I say there is a 60% chance of rain, what would be the chance of no rain? Well, 100% is everything happening, so 60% is rain, 40% should be no rain. So the not having rain would be 40%. Now, it doesn't say it's going to be sunny, it could be cloudy. It's just the probability of either something happening, rain, or not raining. There it is. Now, I don't know what you call snow. Usually they refer to just precipitation, but we'll call it. But there's always this total between something happening and not happening has to be 100%. And when you look at the number 1, that is 100%. So when you subtract off the probability of something happened, 100 minus what the probability of it happening, that's the probability of it not happening. So again, we could look at it as percentages. These formulas typically look at it as decimals. So 60% would get represented as 0.6, 40% would be 0.4. So that's the case that's going on. It's just a lot of times easier to think, at least for me, in terms of percentages. So the same thing happens as something not happening, subtracted from 100%, you get the probability of it happening. So whichever I tell you, take it up from 100%. And then some other notation. Remember we talked about the complement before. Complement is something happening or not happening. And E little prime is the complement, so it means not happening. A lot of different ways to say exactly the same thing. Okay, so when we're dealing with cards, now with rain, 60% rain, 40% not raining, what we deal with, the probability of not getting a queen, well, that would be 1 or 100% minus the probability of getting a queen. The probability of getting a queen on a deck of cards, there you could think of it, there are 4 queens out of 52 cards, which reduces down to 1/13. And the reason they look at 1 is you can think of 100% as whatever your common denominator is, 13 out of 13. So if it's got a 1/13th chance of getting a queen, you've got a 12/13th chance of not getting a queen. Okay, so just quick and easy. You don't have to go through and count all the ways of not getting a queen. It's the easier thing to do, count how do I get a queen? Well, there's only 4 out of 52 queens. So not getting a queen is going to be 1 minus that. Okay, pretty much how it goes. Now with or probability, there's 2 types of things that happen. We get mutually exclusive events, or we get events that are not mutually exclusive. So mutually exclusive events simply means that if one thing happens, it doesn't affect how the other is going to happen. So maybe like flipping a coin, getting a heads or tails is one thing that could happen, drawing a card out, but they're completely different. It doesn't matter whether you got a heads or a tails, depending upon what what you drew out of a deck of cards. So the difference is we have to, when we go through this, we have to decide whether the events are mutually exclusive or not. If they are, we just add the two probabilities together. Probability of flipping a coin and getting a head is 50%. Probability of drawing a queen out of a deck of cards is 4 out of 52. Just add them together, and that will be the OR probability. So one card is randomly selected from a deck of cards. What is the probability of selecting a king or a queen? Mutually exclusive, as long as, well, because we're only selecting one card, right? I was going to say as long as the card's replaced, but we're just selecting, and we want either a king or a queen. So just like you think, we would add both probabilities together. There's 4 kings, 4 queens, so the total would be 8 out of 52, which reduces down to 2/13. Okay. Now, with events that are not mutually exclusive, so we're going to look at what would that mean. So they're not mutually exclusive if they could both occur together. Okay, so we're going to take a look at what that means, and we'll go to a deck of cards. It might be like, what's the probability of drawing a clubs, and then what's the probability of drawing a jack. There's a jack that's also a club, so that's not mutually exclusive. There's a card that has sort of both qualities. So what we do is we add them together, but we subtract off the overlap, and we're going to see that next. Okay, so just add the two probabilities, subtract the overlapping or the intersecting characteristic, the cards. So in a group of 25 baboons, 18 enjoy grooming their neighbors, 16 enjoy screeching wildly, while 10 enjoy doing both. So you see, these 10 are in both groups. So if you were to kind of draw this, remember Venn diagrams is kind of helpful. We've got the groomers, and again, there's 18, but remember, they include 10 here. So there's 10 that enjoy doing both. So there's 8 that only like grooming, but here's the 18 that would like grooming. Okay. Over here, the ones that like screeching wildly, we've already counted for 10 of them, so there's another 6 here. So notice this is the part that is not mutually exclusive. So what do we have to do? 12. So let's see, find the probability so one baboon is selected at random that enjoys grooming its neighbors or screeching wildly. Well, in this case, we could just say, well, let's see, how many have we counted? We've counted a total of 10. There's 18 plus 6 more would be 24. 18 plus 6 is 24. Right, or 16 plus 8, that's going to give us 24 total. So we could also apply the 1. So there's one baboon that doesn't enjoy doing either of them. But the way using the formulas is we're going to say, well, the ones that enjoy grooming would be 18 out of 25. We're going to add to those that enjoy screeching wildly, which is 16 out of 25. And then we're going to subtract off the overlap, because what happened is we counted those 10 twice. We counted them here and here. So we subtract them off. Okay, you'll see how that does it. Another way to do this, if you can make these tables, and it makes a little bit more sense to me, is I would have added 8 out of 25 for those who just like grooming. I might have added the 6 out of 25 that like to scream wildly and only like to scream, and then we could add the 10 separately. Okay, notice we'll get the same value in both places. Here we get 24 out of 25. Here we overcount, we get 34. 34 minus 10 gives us the 24. Okay. So I'm going to click through and it will do the counting for us, the 18 out of 25, the 16 out of 25, and then subtract the 10 out of 25. Total 24 out of 25. However you do it, we don't have 34 baboons, so it wouldn't make sense to get 34 out of 25. So this is a non-mutually exclusive, not mutually exclusive, because there's some baboons that are in both groups. Okay. So we've covered two parts already. We've covered the not probability. We've covered the or probability. And remember, there's sort of two different things. One, if they're mutually exclusive, we just say, okay, add them together. But we're careful because we know we're not double counting something. The ones that are not mutually exclusive, what we have to do is we have to think, is there a possibility that I'm double counting? Is there somebody that's in both groups? Okay, so that's where the Venn diagrams become helpful. Now, this is the last concept we have for 11.6, and that's this concept of odds. Now, odds is used oftentimes in sports gaming, sports betting, the odds of something happening. It's horse racing, dog racing, those kind of things. They keep track of things by odds, because what the odds are is not the total, it's how many things, the probability of event. So we know the probability of event, we can determine the odds in favor and the odds against. So the odds in favor, notice it's not totals, it's the probability. Well, they use it in terms of probability, which when I think of odds, what I want to do is think of sports, you either win or you lose. So yeah, sometimes you tie, but so it's usually presented as wins versus losses. And if you total the game, if you total the wins and losses together, you get the total number of games. Sometimes what they'll do is a tie, they'll count as either a half a win or a half a loss or something. I don't know what they do. But odds are really just set up for two things. You either win or you lose. So it's number of wins, number of losses. So that's the way I'm going to look at it. I don't like using it as a fraction because you notice it actually can be over 100%. I mean, one could be bigger than the other. So odds against and odds for, but I just like to think odds against, odds in favor of something is wins to losses. Odds against something happening are the number of losses compared to the number of wins. You just flip it this way. So odds against E can also be found by reversing the ratio, right? Just reverse it, okay, representing the odds. So I prefer personally using the ratio format, and it helps you understand that you're not dealing with a probability. It's just too easy to confuse these. And I remember when I was a math major, back in college, lived in Portland, Oregon. Went to Portland State University for a while. We had dog racing. It was kind of fun. Go out Friday night, Saturday night, whatever. Watch the dogs run and kind of bet on them. And one time I made some money, so I thought that was great. I got lucky. But one of the things I realized once I started studying, I took a class on probability, was that I was reading the race form wrong. I was reading it as if it were probabilities and doing the calculating, think I was really good, but they weren't. They were odds. I needed to do odds, so I was way off. That's why that time I lost. Well, I lost everything, $20. Doesn't seem like a lot now, but back in the '80s, that was a lot of money. I was making $2 an hour, or maybe it was $2.50, but not much more than that. Okay, so probability odds. It's also counting, but what we're counting is sort of wins to losses. So let E represent the event of rolling a 2. Find the probability of E occurring and the probability of E not occurring. Again, I'm not going to worry about this part of it. We could, probability of E occurring, a 2 is 1 out of 6. Probability of not occurring is going to be 5 out of 6. Okay. And so you could say the odds are 1/5, but I want to do this differently. I want to just count. How many 2s are there? There is 1. How many not 2s are there? There's 1, 2, 3, 4, 5. There's 5. So the what are we looking for? The odds in favor of rolling a 2. Well, there's 1 2, and there's 5 that are not 2s. This is the way my preference is. Don't go to probabilities because it just confuses you. It's extra steps. Let's just count. There is 1 2. That's 1. And there's 5 that are not 2s. 5. 1 to 5. That is what odds are. Don't even go this route. This is too much. Someone who's been doing math too long. Okay. We get to the same answer. And again, you look at this and then you start thinking of that as a probability. You think of that as 1/5 is 20%, but you're completely wrong. And you can be very more wrong, because if they do the opposite, it would be what's the favor, the odds against. A lot of times they want that. That's going to be just 5 to 1. And if you do odds against, what you do is you would have got 5 over 1, which is 5. And so, is that 500%? No, it's not. Percentages don't, when you're doing odds, just don't do percentages. Don't do fractions, do ratios. So this is odds for, and this is odds against. Odds. Okay, so you first count how many are not 2s. How many guys are against you. There's 5. There's only 1 for you. So that's 5 to 1 odds against, 1 to 5 odds for. So they think of, they use terms like odds on favorite and odds against favorite, but that's what they do with odds. Okay. You can do the conversion. So notice, let's come back here. If I wanted to convert this to a probability, you just have to remember that odds, I have to add them together to get the total. And that probability is always sort of number 4 over the total. Odds are not the total, but I can get the total by adding it because it's got everything here, 6. So the probability would have been 1 out of 6. We got that right here, right? So 1/6 is the probability, 1 to 5 is the odds. And again, I don't even like looking at these numbers here, because looking at it as a fraction makes you want to turn it to a decimal, and it's a different way of doing the counting. Okay, but we can get there. So that's all this means is, just count differently. Just count differently. Okay. The odds in favor of a particular horse winning a race are 2 to 5. Okay, so let's just gonna agree with each other. Odds for are 2 to 5. Let's write it as a ratio, because odds in favor A to B means a probability of that. The odds in favor of 2 to 5, blah, blah, blah. Again, what does it mean? Well, 2 to 5 means that when there are 7 races, the horse will win 2 times, it'll lose 5 times. That's what odds are telling you. So when you want to go to a probability of winning, well, there's 2 times that it wins out of, yes, 2 plus 5, 2/7. So if you want to deal with a probability, that's it. You can turn 2/7 into a percentage. Again, it's got it down here. And sometimes that helps, that when you're working with probability, as you notice, I've done it. I like working with percentages. So 2 divided by 7. Let's just bring it back over here. 2 divided by 7, because we're dealing with probabilities now. That's about 28.5%, maybe 29 if you want to round it up. Let's shrink it down. So let's call it 28.6% chance. I'm thinking almost 30% is what I would think of. But a lot of sports bettors, what they get used to doing is dealing with odds, and in their mind, they have this feeling that that's about a 30% chance. Okay. But if you were like me, I took 2 divided by 5, and I have 40%. I thought I had a 40% chance of winning when I really only have a 28.6% chance. You see how this could become very confusing. So be careful. Odds and probabilities are different ways of representing sort of the same thing of what's the chance of something happening, but you get different numbers. We're done with 11.6. So the homework will take you through that. Just really highlight when you see the word, let me go back. When you're reading, whenever you see the word odds, underline it, or at least in your mind, that odds, oh, that's something different. I need to count. I need to count how many ways of winning, how many ways of losing, and then I get a ratio. It's not probabilities. Okay. So now we're going to conclude with and events. So this is conditional probability. That conditional means something has to happen first and then this happens. So I brought my umbrella. What's the chance of rain on the day that I brought my umbrella? You say, I forgot my umbrella. That's the days it always rains, something like that. So conditional probability. Okay, so we're going to do both. So and probabilities, this is two things happening kind of together. Again, it's going to be a multiplication because we need two things to happen. And if you're familiar, when you're multiplying decimals less than one, the probabilities will actually be smaller than just one thing happening. Probably like this happening, okay, that's 30%. But the probability of two things happening together, the probabilities are actually going to get reduced. But there are two different, just as with the or probabilities, there's two different things. One is, are the events completely independent? Or is there some overlap? If one happening going to make the other more likely? Okay, I don't know that bringing my umbrella makes rain either more or less likely, but sometimes some events, one event couldn't happen unless you're there. The probability of me being at the coffee shop and the probability of me meeting my friend at the coffee shop. Well, if I'm not at the coffee shop, I can't meet my friend at the coffee shop. So there's some overlap there. Okay, so independent events on a roulette wheel. So independent means one thing happening doesn't create the others. Okay, so there's 38 numbers on a roulette wheel, 1 through 36, and then you get a 0 and a 0, 0. We've got 18 black, 18 red, 2 are green. The ball can only land on any slot with equal probability. Okay, so it goes around and lands on a slot, but it can only land in one. What is the probability of red occurring on 2 consecutive plays? Okay, so getting red 2 times in a row. Now, are those independent? I do it the first time. Has that changed the probability? No, because when I do it again, the wheel's the same. It's still got the same probability of falling on any particular one. So a red, there's 18 reds. And there's 38. Let's see, probably of a red occurring on a play is 18 out of 32. So then that's why they reduce. I hate when they reduce it because I can see the 18 out of 38, but why do we need to reduce it when we're going to turn it to a decimal at the end anyway? So yeah, 9/19 times 9/19. Again, I would have done 18/38 times 18/38. And then I would have multiplied these. I would have turned it to a decimal. I would have got the same decimal without having to go through this extra mathematical steps. Okay, so for getting them both in a row, it's 22.4%. Now, what is 18 out of 38? What is it? The probability of just getting a red one time? Let's do that one. 18 divided by 38. That's why I like percentages. I can always look at it. Notice I had a 47% chance, 47.3% chance of getting a red the first time. But now to do it 2 times in a row is a lower probability. That makes sense, doesn't it? In fact, it's more than half, less than half. Okay, so it's going to reduce. But it's just remember with and probabilities, we multiply the 2 probabilities of one thing occurring times a second. Independent events in a family. So this is one getting 9 girls in a row, 9 children, that's a lot. So there's a 50% chance of getting a girl, and that's an assumption. Actually, I think there's a slightly higher chance of getting a girl than a boy. But it's like 50 point something. But they go, okay, so it's half and half. So the first girl is half, and so getting 9 girls would be 1/2 to the 9th. So if you know a family that has 9 girls, has had 9 kids, and each of them are all girls, it's a very rare event. But it could happen. It could happen, right? Let me plug in my battery. There we go. Now we're not running low. Okay. Maybe I should have made 2 different videos, but we're doing okay, aren't we? Okay. You'd always fast forward. Okay, hurricanes and probability. So if the probability that South Florida will be hit by a hurricane in any single year is 5/19, what is the probability that South Florida will be hit by a hurricane in 3 consecutive years? Again, why do we have to go to this? But the idea is that just because we got a hurricane in one year doesn't change the hurricane in the next. And that's the thing is, they'll talk about these 100-year floods or something. And just because you had it this year doesn't mean you couldn't have another 100-year flood next year. They happen on average every 100 years, but you still could have one. Fortunately, they don't usually do that, but it's possible. It's a low probability that we would get 3 hurricanes in a row, but it could happen. Less than 2%. Okay, but just the thing we have to remember, it's the multiplication principle. Just multiply them all together, and having a hurricane one year really doesn't affect the next. Okay. Now, what's the probability of no hurricanes? Again, you take 1 minus the probability of having a hurricane. There's actually a 73% chance of not having a hurricane. The probability of not being hit by a hurricane in a single year is 14/19. So what's the probability of not being hit by a hurricane 10 years in a row? That's also a fairly small amount. Okay. And again, the fact that we didn't have a hurricane this year does not increase or decrease the probability in the following year. Each year is kind of like a new set. Okay, so these give some examples of how we can go through these calculations. Now we talked about independent events, ones that do not affect the probability of the others. Now let's talk about dependent events. And this is going to help us as we move towards conditional probability. So the probabilities with ands, it's still multiplication, but what happens, it's the probability of the first event happening, and then it's multiplied times the second event given that the first event occurred. Because if A didn't occur, A and B is not going to occur, right? If I didn't go to the coffee shop, I'm not going to meet my friend at the coffee shop. Okay, so A has to have happened. So this is what we call a conditional probability. And again, it comes back down to counting. Okay, so an event we're going to do. You have won a free trip to Madrid and you take 2 people, all expenses paid. Bad news, 10 of your cousins have appeared out of nowhere and are begging you to take them. You write each cousin's name on a card. So there's how many? 10. Place the cards in a hat and select one name. Then you select a second name without replacing the first card. See, so the hat has changed. How many are in there now? There's only 9, right? Because we took one out. If 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins. Okay, so we're going to take 2 people with you, all expenses paid. So we get 2 to go with us. We're going to choose from 10, and this is kind of our counting thing. So we're starting off with 3 out of the 10 speak Spanish. So this is the probability of getting the first one, choosing the first one as one being a Spanish-speaking cousin. So that would be, there's 3 of them out of 10. Now this is the same thing for the second one. We have to assume that the first one spoke Spanish. So now how many Spanish-speaking cousins do we have? We've only got 2, and out of a group of 9 because we chose one. Okay, so this is the conditional. We assume that the first one was a Spanish-speaking, because if they weren't, this event would not happen. We wouldn't get 2 in a row. Okay, so then it's just multiplying the probabilities together. 3 times 2 is 6 over 90. So we've got a, out of that grouping, even though 3 of them, I would just say, okay, who speaks Spanish? Those are the ones I want to take with me, both of them. So I would have been choosing out of 3 cousins, right? 67%. Okay, so get the idea of this dependent events. The second event depended upon the first one. Okay, and the ways it's phrased, we want the probability that both speak Spanish. So the second one speaks Spanish, given that a Spanish-speaking cousin was selected first. Okay, let's see this one. We're going to, again, it's just think of it as counting. We're going to be counting. 3 people are randomly selected, so we're going to have 3 choices, right? Here's 1, 2, 3. 1 person at a time. We've got 5 freshmen, 2 sophomores, 4 juniors. Okay, find the probability that the first 2 people selected are freshmen. First 2 are freshmen, and the third is junior. So we're going to get, you could look down here, but the first one, we're going to be choosing from these 5 freshmen. So we randomly choose, we've got 5 of them to choose from, but how many? We've got a total of 5 plus 2 plus 4, which is, that's 6, that's 11. So we're choosing out of 11 people, what's the probability get that one of them is a freshman? We 5 11s. For the second one, since we have to assume we chose a freshman, so we're down to 4 out of 10. See, it's just like doing permutations, really. And then the third one is a junior, so we're choosing out of these 4. There's 4 juniors left, but now how many total people? Not 10, we chose 1 here, so there's only 9 total people, right? So they explained that down here, but I just kind of want you to sort of think how you're doing this counting. We're going to count down and we multiply. Very similar to what we did with permutations, okay? Multiply the tops, 5 times 10 and 4, and it reduces down to 8 out of 99. Okay, and again, with probabilities, I like turning it into a percentage. I don't know if they did or not, so let's just go to the calculator. To have that particular ordering occur would be 8 divided by 99, little over 8%, 8.0. So we could say maybe 8.1%. Okay. So conditional probability, that's kind of what we were doing. It's that probability that B happened given that A already happened. We've already been doing that. So it's the way we count things. The probability of event B happening, assuming that event A has already occurred. So let's back up. Oops, I'm going the wrong way. So recognize this was a conditional probability. This was a conditional probability. Okay. Freshman, given that the first one. So we knew that this happened. So notice we just have to be careful how we count. Okay. So we're looking, so letters randomly selected from the letters of the English alphabet. Boom. So 26 letters, 24. I forget. It should be 26, right? Find the probability of selecting a vowel given that the outcome is a letter that precedes H. Given that the outcome is a letter that precedes H. So all we're going to do is how we're counting, we can count on that the letter is before H. So vowel for a letter that precedes H. So what we have to do is count how many letters precede H. Well, that's 1, 2, 3, 4, 5, 6, 7. So that's the total. How many of those are vowels? Well, A is a vowel and E is a vowel. So that's going to be 2/7. That's conditional probability. We have additional information that tells us something has already happened, and we use that to calculate our probability. Okay, so let's see 2/7 here. They explain it all, but just like we did, we counted. There's two vowels, E and A and E. There's a total of 7 possible outcomes, 7 letters before H, and so it's just 2/7. That's all a conditional probability is you just have to think. I have to count carefully. Okay, and now this is where it gets a little bit more complicated. I'll do a few of these, but assuming these numbers are representative of all U.S. women ages from 40 to 50, find the probability that a woman in this age range has a positive mammogram given, so this is the information we already know, that she does not have breast cancer. So we know she does not have breast cancer. No breast cancer. So what we're doing is it just tells us we know that we're dealing with these numbers. The numbers about breast cancer, this doesn't matter. We're just dealing with the no breast. This is the field we're in. And we want to know what percentage would have a probability of having a positive mammogram. So that would be these here out of this total, right? 6,944 out of 992. Just a matter of counting. We don't do it out of 100,000. We don't do it out of here. We know that because we've got the given that the woman does not have breast cancer. Okay, so 690. So it's still possible to have a positive mammogram though without having breast cancer. So again, you just take from the chart. You could add these two, but again, it's got the total here. It's got this. We're just dealing with this group. So the rest of the table, we don't even consider. Okay, so that's what we're doing with this. Now, it's not saying that this is just answering the question that what's a probability, what's a percentage that a woman who has a positive mammogram does not have breast cancer. Actually, it's the other way around, that she doesn't have breast cancer, but she got a positive mammogram. That could happen 7% of the time. No breast cancer, but positive. Okay. You can also use that to calculate other things, and that's why, even a test that is very accurate, as you can see out of 100,000 here, the percentage, 720 out of 800, so, usually if you have a positive test, most of the ones that have a positive test, at least, they did have 720 out of 800. The ones we got to worry about, though, is that they came back with a negative. 80 people came back with negative, but they actually had cancer. That would be detected probably later. But these ones that get a positive test result, 7% of them, they're really worried that that this is a terrible thing that happened to them, but they actually don't have it. The good news is a lot of times that can be caught on a second, and hopefully caught on a second test. That's why you want to get a second opinion. Okay, so work through the problems. This is the end of our probability unit. It really encompasses everything with figuring out the probability of something happening. Next, we go into statistics, which involves counting and data again, and then we use some of these principles from probability to see, is something happening by chance, or is there like something different? If we use the statistics, say, hey, this is happening more than we would expect by chance, so there's a reason for this. And we'll take a look at that starting on Thursday and going through next week. Take care, work through the problems, and let me know if you have any questions. Thanks.